This video, I'm going to attempt to find the geometric algebra equivalence to some dyadic notation that was brought to my attention in some correspondence. We have here a tensor product, the gradient times a vector, or the direct product of a gradient times a vector. That can be written out here in a matrix form, where we have the ddxi row and the vj column, so v1, v2, v3 columns, ddx1, ddx2, ddx3 as the row entries of this particular matrix. Now, apparently in this dyadic notation, you can write the differential of a vector v in this form of the direct product of the gradient and the vector transposed, dotted with dr. And there's an alternate form that's used in some of the notation. I think this is the one that was claimed to be the correct version and this incorrect, and that both can be found in the literature. Now, the other part of this exercise is to find the geometric algebra equivalence to this symmetric and antisymmetric decomposition of these products. Now, it seems to me that this transpose must actually apply to the entire tensor product, so that, because it just doesn't make sense to transpose just a vector in this sense, I don't think. So I think that what we want is that that is what is being considered. And then the second product, omega, the antisymmetrization of this product, is considered to be a traceless and transpose inverse matrix. So it's a bivector equivalent. So let's go through this exercise. I'm going to start with differential in this form, and let's see here if we can figure out what that means. So if we have dv equals direct product v transposed dr, and we're writing the direct product in matrix form as ddx I vj, the matrix of these elements. So that is ddxi vj transposed dr, or dxj vi, and dotting this, I'm assuming we vary the j index, so that means drj. And all right, something is a little off here because this is a scalar relationship, whereas we start with a vector relationship. The differential of vector is still a vector, so it must mean that we want to say ei, where ei is the e1, e2, e3 is an orthonormal basis for R3. So assuming that this is what we mean, so this is ddxj drj times vi ei, where I'm implicitly summing over all indices, over all repeated indices, and so that is dr dot grad scalar operator times v, the vector. So that's not an unreasonable quantity to be investigating. This is like the part of a component of the convective derivative. So when if we take a function, let's say take the derivative of a with respect to time, where a is a function of, let's say, r and t, well, what is that? That's dA dt partial plus dA dx I dx I dt, and which is, we could say dA dt plus E dot grad A. So we see quantities like this in fluid dynamics and other parts of physics. So having a operator V dot grad, or in differential form, if we have no time dependence, then we might say that dA is just V dt dot grad, all operating on A, and that is what we call dr. So this quantity that we found here, attempting to interpret the tensor product notation, is a reasonable quantity, reasonable physical quantity. And so let's look at this as our interpretation of what we mean by dV. And here, up here, v is just a vector, whereas here v is the velocity. And so we avoid the ambiguous notation by calling this quantity v dt dr, just the variation of the x vector. Anyways, so if we have a non-dyadic interpretation of our dyadic quantity, so we're assuming this was equivalent to grad v dot dr. So whatever this dyadic notation is, this is what I'm assuming it to actually mean. So this convective derivative is easy enough to interpret. So let's now go and see if we can symmetrize and anti-symmetrize this. I want to expand this out in a way that we can regroup our terms in different orders. And so if we have, I'm going to write again, dV equals dr dot grad v. All right. So how can we regroup so that grad is applied to v as a separate, and then that we have some sort of multiplication by dr. So I will go and rewrite this. We have a scalar operator times a vector, so our result is a vector. If we treat this vector as a multivector and then select just the grade 1 component, we don't change our result at all. So we can say that is the same as dr dot grad v, all enclosed in a grade 1 selection. So we are selecting the vector component of this multi-vector, and this multi-vector happens to be a vector, so we don't change the result at all by doing that. Now if we do that, we can make use of the fact that we have two vectors, a, b, that's a dot b plus a wedge b, and if we have a dot product, we can then rewrite the dot product in terms of the vector product and the wedge product. So let's do that. So we have here dr grad minus dr wedge grad, all operating on v, all within a grade 1 selection. So now we can look at these terms here. So we have a bivector times a vector. When we multiply a bivector by a vector, we end up with one vector component and one trivector component, and we're filtering out only the vector components, so the trivector component vanishes, and when we have, let's say, bivector b times v, that's b dotted with v plus b wedge v, this is the vector component, this is the trivector component. We're saying that the trivector component of this is killed by our vector selection, so we're just left with the b dot v term. So that is the dr grad v, the vector component of this multi-vector product, minus dr wedge with v, dr wedge with grad dotted with v. All right. And now we can expand this grad v term using our a times b is a dot b plus a wedge b, and what do we get? We have dr times grad dot v plus grad wedge v. Select the vector component. Grad dot v is a scalar, so we have a scalar times a vector, which is a vector. Good, so that just comes out of the scalar of the vector selection. Now we have a vector times a bivector, and the vector's part of that is just the dot product of dr with grad wedge v. So we can write all of this out as dr grad dot v plus dr dotted with grad wedge v and minus dr wedge grad dot v. So this guy here, we have a grad dot v term, which is a symmetric product of the gradient and the vector, which is a scalar, and we have multiplied by dr. And if we are just to write out this guy, that is dr times 1/2 of grad v plus v grad, where grad operates bidirectionally. So in this case, grad operates on v, and here grad is operating on v to the left, and here grad is operating on v to the right. And what we really mean by that is, what do we mean by this? This is v EI DI, where the gradient is operating on V, which is DI V EI. That's what we mean by this particular product. So the differential part commute the differential over to the other side of V, but we have to leave the vector part of the gradient where it is. And so that is what we mean by V grad as opposed to grad V. So we have to allow the gradient to be bidirectionally acting when we put it in this form. So if we go back and look at our goal was to find a symmetrized product of the gradient and the vector as the first term. So it looks like we found that term D. Now we have this guy here to figure out what is this omega, which in this dyadic notation was probably a matrix or something to that effect. All right. So now we want to look at this remaining term, this part here, dr dot grad wedge V minus dr wedge grad dot all dotted with V. So that guy, dr dot dotted with the curl minus dr wedge grad dot V. And it's a little messy, but we can write this all out. And that is, so here we're going to use another identity. We have A time dotted with B wedge C, and these are all vectors. Then that is A dot B C minus, and then so we plus and minus A dot C B. So that's how we distribute our dot product, vector by vector dot product. It's in this particular form. We use this identity, and we can rewrite this all out as dr dot grad V minus dr dot V grad, and here grad operates on V. So grad is operating on V to the left. Here grad is operating on V to the right. And we have some more terms. We have, just like if we have here B wedge C dot with A, that is going to be B A dot C minus A dot B C. So we use the same distribution rules, and we are left with grad dot V all times dr plus dr dot V grad. Set. And it doesn't matter which order we use because this is a scalar, so we can just put our grad here on the opposite side where we're used to it, knowing that this grad is operating on V and it's not operating on dr. We have a divergence term, and so dr dot grad dr dot, we have dr dot V grad, so we'll put our grad over here. Those terms cancel, we're left with dr dot grad v minus dr dot grad dot v. So can we simplify that even further? And we can, the easy way to do that is to notice that this is exactly this form. So this has the form of grad v. So dr dot grad wedge v. So dr dot grad times v, dr dot grad times dr times grad times v, which is our term here, minus dr dot, right. No, that's not it. All right, let's try again. We have dr wedge v grad dot. So now we have grad dot dr times v, grad dot dr times v minus grad dot v times dr. Good. Okay, that's it. All right. So now we have, that's the final result is that dv equals dr grad dot v plus grad dot dr wedge v. Which is just a rather complicated way of writing dr dot grad operating on v. However, this has the possible benefit of splitting this differential into a term that has a gradient and splitting this into a term that is not the gradient, but is dr wedge v. So if we have dr and v, dr wedge v is this plane, and then we take the dot product of the gradient with that plane as one of the components of our differential. Actually, I got the sign of that wrong with how I drew it. So it's like dr and v. So dr wedge v has this orientation. All right, so that is our symmetry term and our antisymmetric term. We've found that those are the equivalents of, here's our symmetric term and our antisymmetric term. So our geometric algebra equivalents to this expression are just a divergence and this beastie. And as an operator, I suppose, yeah, it's not the most obvious what to call this thing and exactly what it is. One thing we could do is we could go full circle and put this back into Gibbs form. Let's do that just to see how to give us another interpretation of this abstract divergence. So if we have grad dotted with dr wedge v, well, okay, so dr wedge v is a bivector, this is a vector, the dot product is the vector term of that product. So that is the vector term of dr wedge v. Here we select the vector term of this multivector product. And if we do that, we can, since we're in R3, we can rewrite this as I dr cross v 1. And I commutes with the gradient, so we can move that to the other side. And then the gradient is a vector times a vector that has a scalar component and a bivector component. So let's just write this out. I times grad dotted with dr cross v plus grad wedged with dr cross v and brace scalar select. Now, this is a scalar, grade 0. This is trivector, grade 3. The product of the two is a trivector. So since we are selecting the vector component of this multivector, this term is killed. So we're left with a wedge product times the pseudoscalar, which is I squared grad crossed with dr cross v. 1. And I squared is minus 1. So that is grad cross v cross dr. All right, so here is the traditional vector analysis equivalent of this divergence, this bivector divergence. It is the triple cross of gradient v and dr. All right, so those are different interpretations. So we could write dv as dr grad dot v plus grad cross v dot v cross dr. There's another way of writing this particular differential. And the antisymmetry that was being desired is clearly in effect when we have cross products and cross products in this curl. All right, that's it. I think that's just about everything to say about extracting the GA form of the differential of a vector, which is just this convective-like derivative. And then we can also, if we desire, we can put that into strictly vector format, like so. But then we have to deal with multiple cross products, which is arguably less intuitive than just a vector by vector dot product.